How you doing, everybody? Let's take a look at our problem here. We got a mass-mass relationship problem here. Basically, the most fundamental stoichiometry problem that we need to be able to do any type of chemistry, and they'll get progressively more complex. This is just a very basic example. I just sort of made this one up, and we're going to work through it. This will sort of kind of be a review of some basic chemistry, stoichiometry, before we get into some more in-depth stuff. So let's look at our problem here. Calcium hydroxide pellets. That's just extra information, but calcium hydroxide. So if it says pellets, obviously, if it says pellets, then we know that we have a solid, right? So I haven't even read the full problem, and I already know I have solid calcium hydroxide. Just the first three words. They're crushed and then added to a solution of hydrochloric acid. Okay. We don't know how strong, what the concentration is. We just know it's hydrochloric acid, okay? So we're going to add in some hydrochloric acid. And of course, remember that our phase labels, that would be an aqueous solution, right? And so remember, when you have an acid and a base, you should automatically remember an acid and a base that you're going to get water and salt. Those are going to be your products automatically. You should recognize that this right here is kind of a basic double displacement type reaction. Here's your positive cation. Here's the positive cation here in the acid. So remember, you got these free-floating ions here, hydrogen ions and chloride ions. Here you got some calcium ions and hydroxide ions, right? Hydroxide is your anion in this case. So, it's doing some scratch work. So we know calcium is positive 2 ions, and then hydroxide are your negative ions, right? And so then you've got your hydrogen ions and your chloride ions. So this is a double displacement reaction. So what that means is calcium and hydrogen, they displace and then replace each other. And specifically, if you go to your reference sheet, okay, if you go to your reference sheet and look over here, you can see on your, let me move myself out of the way for you. You can see right here that the calcium, it reacts with oxides, reacts with cold water and acids. Okay, so we know it's going to react with that, and it replaces hydrogen. All right, so it's replacing the hydrogen. It's reacting with the hydrogen in the hydrochloric acid and replacing it. All right. Another way, if you weren't too terribly sure, then if it was going to work, would be to come back here to your solubility rules. So if we come over here, right, and then we zoom in a little bit, right, then let me zoom out a little bit for you right here. You can see right here your hydroxide. All right, typically those are insoluble, except when it's with calcium. All right, so right here we can see that this would solubilize, it would mix with it, and we can get that reaction going. And then what we got to do is just basically figure out, what's happening from here. Well, calcium is over here with chlorine. So your calcium ions are over here with your chloride ions, and then your hydrogen ions are over here with your hydroxide ions, right? So what I'm doing is just scratch work. This would be in the scratch work area, not in the region where you would do something for a test or whatever, unless you were specifically told to show the work in that space. This is like scratch work. So you can see right here, positive 2, negative 1. So you would need 2 of these and 1 of these. So we know that we get calcium chloride, okay? And then obviously right here, this is H2O. And of course, H2O will be in a liquid phase. It's not hot enough for a vapor, it's not cold enough for a solid. And then calcium chloride, it's going to be dissolved in here. If we know that this would mix with this and dissolve, this is not going to precipitate out. So we know that we would get an aqueous solution. Okay. So now let's come over here. Let's let's get all this scratch work out of the way. Kind of clear that mess up a little bit. Go back here, and let's see about getting some work done here. All right, so we've got our reaction. Now we look at this and we go, you know, we've got to balance it out. Before you can do anything, you always have to balance it out. So you look here, you see there's 2 chlorines here, 1 chlorine there. So more than likely, we're going to have to put a 2 here to get this balanced. Let me put that in a better place for you. 2 chlorines here, 2 chlorines here. Chlorines are good, check. 1 calcium, check. So now we have 2 hydrogens here plus, oh, I wrote that wrong. I'm just now noticing this. So if you picked up on this, good job. In my rush to do this, I thought I wrote this, but there has to be a 2 there because this is a solid. There has to be a subscript of 2 right here for this to exist, because you need 2 hydroxide ions, right? This was positive 2, this is negative 1. So in my mind, I thought I wrote it, but I'm now catching it. So luckily, if they were doing this for a quiz or a test, I'd have caught myself in time before I lost points. Okay, so now we're back. 2 hydrogens right here, and then there's a 2 here. This 2 says 2 of everything in parentheses, right? So that means there's 2 hydrogens here, 2 hydrogens, that's 4 hydrogens. That also means there's 2 oxygens right here. So the way we can resolve that is to come up here and add a coefficient of 2, and now we have a balanced chemical equation. Now we have something we can work with. All right. So just to review, we had our base. This is our base, calcium hydroxide. Remember, hydroxide typically are your bases. Hydrochloric acid. Move my coffee over here where I can get to it a little more easily. I love that coffee. So anyway, and then double displacement reaction gave us our calcium chloride, our aqueous salt, and then water. So if we were in lab, we could carry out this reaction. Then we would have, in a container, we would basically have salt water, and we could apply heat to that, push the liquid water into a gaseous phase, water vapor. It would escape, it go up into the atmosphere, and then since there would be no water, as that water escapes and there's not enough, these ions here would have no choice but to resociate back into their solid state, and we would get solid calcium chloride that would precipitate out of the heat reaction. All right. Okay, so now this problem says we got 4 grams of the base substance. All right, so that means we've got 4 grams of the base substance. How much salt will be made? So then we have another thing here. It says, following the law of conservation math, how much water we will be producing reaction. So obviously, we're also going to need a question mark here as well. Okay. All right. So let's get started with our stoichiometry. You should remember, always start with what you're given. So we've got 4 grams of our calcium hydroxide. Remember the 2 this time. Okay. And then, so what we need now is we need our molar mass. So remember, we've got 1 calcium, 2 oxygens, and 2 hydrogens. And so what I'm going to want you to do is, so there's your calcium. So you see how it says 40.078. There's nothing wrong with using all the numbers and doing your calculations from there. Typically in class, because of the equipment that we have, I'm going to add, and our equipment, the uncertainty, the estimated digit that we have to make is in the 100th place. So since it's in the 100th place, what I'm going to want us to do, which helps with eliminating error with the labs that we do, will be to round all of these numbers on the periodic table to the nearest 100th. So for calcium, you're going to use 40.08, okay? And then we've got calcium hydroxide, so we've got oxygen. So you can see oxygen right here, 15.99. So this 9 would round that 9 up, so this would be 16.00, right? And then hydrogen, 1.008. Obviously, it's going to be 1.01. Okay, I'm going to want you to do that for everything that we do in class as far as periodic table and our calculations goes. Okay. So we look at that and we realize that our calcium was, what did we say it was on there? So that was 0.8 plus 2. You should get 74.10. And your calculator says 74.1, but we need the 0, remember, for sig figs. That'd be grams of calcium hydroxide. And of course, that's going to be the molar mass, so we know that's for every 1 mole, right? And then let's go ahead and cancel out our units. Canceling out units is essential. All right. Bring this down. See, we've got calcium hydroxide. So we're bringing down the mole of it. So we can see here we have 1 mole of calcium hydroxide for every 1 mole of calcium chloride. So the ratio is 1 to 1. I know it's just ones, but you have to write every single step because it's not always a coefficient of 1. All right, of the calcium chloride, right? So I just want to shrink this a little bit. I really like OneNote. It's a very lightweight but very versatile program. I like it a lot. So now we need to bring moles of calcium chloride down. All right. So we need to know the molar mass for calcium chloride. So again, you go back to your periodic table. We already know calcium. We already said was 40.08. And then chlorine, we need to find our chlorine, 35.453. So we're going to go with 35.45. Okay. All right. We're going to go with 35.45, right? So 0.08 plus, do this with me, 35.45 times 2. It gives us 110.98. So we've got 100, what did I say? Yeah, 110.98 grams of calcium chloride. All right, that's kind of messy looking. I expect your work to be better than that. So the least I can do is to try to do the same for you. And let's get rid of our units. We forgot to get rid of them there. By we, I mean me. All right. Now it's just a matter of plugging and chugging. So we got 110.98 times 4 on the numerator divided by our 74.1. Should get 5.99082. You just need some extra numbers. Grams of calcium chloride. So 4.003 sig figs. Let's go with 3 sig figs here. Let's see what happens. 1, 2, 3. 0 will not round that up. So 5.99 grams of calcium chloride. That's our answer. Not 6.00, 5.99, because this 0 does not round that up. It's not significantly high enough, that 0. So it has to stay 5.99. You don't write 6. Okay. All right, so now it looks like we did the first part of this. It says how much salt we produce. This assumes 100% efficiency. This assumes that everything in the reaction goes the way it's supposed to. There's no error whatsoever, which is very possible to do. People do it all the time. So now the next part says, following the law of conservation mass, how much water will be produced in reaction. It's the same basic stoichiometry problem. We're going to start with 4 grams, and we're going to do all of our work to right here to the water. All right. So we've got 4.00 grams of calcium hydroxide. We already know from here that there's a ratio of 74.10 grams of the calcium hydroxide for every mole of this substance. Okay. All right. Bring this down, and now what we need to do is we realize, okay, so we've got 1 mole of calcium hydroxide for every 2 moles of water. So that ratio we must show. So we'll bring this down. We know that there's 1 mole of calcium hydroxide for every 2 moles of water. Okay. Cancel out those units. Got to cancel out those units. It's very important. All right, 1 mole of water. So oxygen 16, hydrogen 1.01. There's 2 of those. So that's 2.02 plus 16. Don't need a calculator for this one. So 18.02 grams of water. That's the molar mass. So let's go ahead and cancel all that out. Now it's just a matter of doing some math. All right, so get out your calculator. 18.02 times 2 times 4. Our numerator, 144.16. Check my math. Divide that by our 74.1. Looks like we get 1.94547. There's a bunch of other numbers. We just need a couple extra. That'd be grams of water. So 3 sig figs up here. Let's go with another 3 sig figs. It'd be 1, 2, 3. We can argue that the 5 would round that up. There's several different rules for that. Essentially, unless we know more. Let me turn this off. I thought I had it on silent. Unless we know. Have more information, another sig fig. We just assume the files will round that up, but they won't always round that up. In a lab situation, it's going to be dependent upon following the law of conservation of mass and looking at your procedures to kind of weigh that out. But for a problem like this, we just assume the 5 rounds it up. So that's going to give us 1.95, because that 5 will round that 4 up, grams of water. Okay. So, following the law of conservation mass, how much water we produce in the reaction? 1.95 grams. All right. So we could follow the basic law of conservation of mass. So we've got calcium hydroxide. I'm not going to worry about phase labels doing this part right here. We've got our hydrochloric acid reacting, and we get calcium chloride plus the water. So we've just found out 1.95 grams of this. Up here we calculated what, 5.99 grams, and we know that we're working with 4 grams of this. So the question is in an ideal situation, what mass of hydrochloric acid would we have? Typically, you don't go by mass for hydrochloric acid. We would go with a certain volume of it and a certain concentration. And I'll take the same problem and I'll incorporate it in some other Stoic problems that we'll do with that. But for the sake of argument, we can just focus on mass. And so according to the law of conservation of mass, we've got 4 grams here plus the mass of hydrochloric acid. It's going to be equal to the 5.99 grams plus the 1.95. It's just like a basic algebraic expression. Both sides, it's an equation, so both sides have to equal each other. So here, of course, you know, if you were in math class, you would subtract 4 from this side. So mass of hydrochloric acid equals 5.99 grams plus 1.95 grams minus the 4 grams we're bringing from the other side. So if you were to do the math on that right here, so 5.99 plus 1.95, that gives you 7.94 minus 4, so that'll give you what, 3.94. So we know that the mass of hydrochloric acid if we were to just look at the mass of it, would be 3.94 grams of substance. And then both sides balance out. And it's going to. If the sides don't balance out in all of the work we do, you've got something wrong somewhere. Either you wrote the formula wrong, and or you've balanced it incorrectly, or you've used some incorrect numbers off of the periodic table, one or more. So those are the places you always check to see where you might have some error. Okay, and that's about it. You could use this as an example. This is a basic guide for pretty much everything. It doesn't matter what the reaction is; it still follows these fundamental principles. All right. Hopefully that helped, and we'll check back in later for another one of these where we take the same problem and just go more in depth with it, get some more detailed information. We're going to find that this procedure works for even those more in-depth problems. We'll just have extra information we're going to add into it. Hope this helped. Hang in there. Talk to you soon. Bye.